Hello, my name is Dan Ambray from Full Spectrum Diagnostics. Today we're going to look at the vibration fault periodic table. The table is a logical visual mapping system to understanding vibration as more systems thinking. We start with 35 common rotating machinery faults, and you see the 35 squares on the table right there. Our first step is to sort the faults for frequency content. This means we want to define how the fault relates to shaft rotating speed. So, as an example, synchronous is turning speed of the shaft. Harmonic is multiples of that synchronous or turning speed. Subsynchronous is faults that appear below 1 times RPM or turning speed of the shaft. Non-synchronous means the opposite of harmonic. There's peaks in the spectrum, but they're not related directly to the shaft. So they're not exactly 3 times or 4 times. They might be 3.68 times running speed. So you have fractions of what that fault might be. And the last is modulation. And modulation is a pulsating event in either amplitude or frequency. And it usually generates some sidebands in the spectrum. So that kind of details what we're looking at. The second sorting mechanism is the dominant directional response, and we have different colors for that. So red is radial dominant response, yellow is axial dominant response, orange can be either. Okay, so when we put our sorting mechanism in, we get the right frequency grouping, we get the right directional response, and then we can perform recommended diagnostics. And the diagnostics are little icons that you can see here at the bottom of the page. If there's a phased icon, there's a time waveform, oil whirl, or orbit analysis, transient analysis, and ultrasonic analysis. Okay, these are also found in the upper right-hand corner of each of these tiles on the table. Okay, so we do a sort by frequency group, we do a directional sort if we can, then we perform the diagnostics on whatever's left on the table. Okay, so we're going to start with that, and we're going to walk through some of the examples here. There we go. Sorry about that. This is our machine. So we take a step back, take a look at it. We're taking data at the 4 positions shown, the red blocks. Our normal detection in the field is remote applications. We bring our box with us, and we take an axial, a horizontal, and vertical measurement at each one of these locations. Okay, the machine is a direct coupled overhung fan. We say that because there's a fault for misalignment, and there's a fault for unbalance, and there's also a fault for an unbalanced overhung fan. And we want to capture both of those types of faults. Turning speed is 1784 RPM. The motor has rolling element bearings. The fan has rolling element bearings, and the fan has 12 blades. Okay, so now we're going to get to the sorting mechanisms. Here's our data that we collect every month. This is one subset of those. So there's 4 different positions on the table, and you can see the little cartoon up here showing the overhung shaft. So positions 1 and 2 are on the motor, 3 and 4 are on the fan bearings. I take data in the axial, horizontal, and vertical directions, and what I'm looking for when I throw all this data back into my database, it compares it to some alarm criteria, and this little stair-step red line is the alarm criteria. If I have a peak that exceeds that line, it's an alarm, and I have to figure out what's going on. Okay, so it's unacceptable. This shows that my turning speed of the shaft at 1784, my 1 times RPM, is in alarm because it exceeds that 1 times RPM threshold level. Okay, I'm showing that same look to the data at position 4. The horizontal direction looks fine, the vertical direction looks fine. So there's something going on in the axial direction at bearings 3 and 4 on the fan, and we know it's in the synchronous grouping. So what does that mean to us? A little clarification here. Synchronous faults, I say 1 times RPM. We determine the rotating speed at 1784 RPM. We put our peak on, or our cursor on whatever the peak is, and determine the machine alarm frequency, which turns out in this case to also be 1784 CPM. The ratio of those two tells us the order of vibration we're looking at. So 1 times RPM is 1784 divided by 1784. So that's a 1-to-1 relationship. Okay, so synchronous fault, it's also called turning speed. There's a lot of different names for it, but we're gonna hang on to synchronous and turning speed, identical things. This is what happens when we determine the frequency grouping. All the other groupings go away. Okay, this is really powerful stuff, because a lot of times if you don't refute something and take it off the table or take it out of your head, you'll be thinking about it and trying to put it back in. In this case, it's a synchronous fault. It's not a harmonic, it's not subsynchronous, it's not non-synchronous, it's not modulation. So all those faults can be grayed out, and we can concentrate on the root causes of the problem. Okay, so there's 11 faults over here in the synchronous columns. The natural frequency is based on mass and stiffness, so it can be anywhere in the spectrum. Okay, so we're going to have to prove that it's not one of these faults, and we're going to have to prove or disprove if a natural frequency is involved. Okay, so we've determined 1 times RPM. The frequency group is whatever the dominant peak is divided by turning speed of the shaft, and in this case it's 1 times RPM then, the 1784. That's our synchronous fault series, and we can move on from there. Okay, now what we're going to look at is a dominant direction, and I have one. I can look radial, those aren't in alarm, so I don't have to deal with that, but in the axial direction, I do have a dominant directional response in the axial plane. So what happens to my table? Those 4 radial vibration events, they're eliminated, okay, because it's not a dominant radial, it's a dominant axial. So that's one of the yellow faults here. I can eliminate a couple other faults, the gear tooth problem and the belt drive problem, because I don't have a gearbox or a belt drive. So now, just looking for the dominant direction, the dominant frequency group, I'm down to 6 different faults, potentially. I look at the upper right-hand corner. This is where my recommended diagnostic comes from. In all 5 of these in the synchronous group in the axial direction have the little phase icon showing up. So I'll do a phase analysis and try to refute or confirm one of these faults, and then I'm going to do a transient analysis to do the same thing over here. So we'll get started. This is our phase bubble chart, or our phase chart, or whatever you want to call it. There's little tick marks on there telling direction and how the machine is moving at turning speed of the shaft. Okay, we won't go all the way through this, but there's faults that appear in red, which are radial faults. There's faults that appear in yellow, which are axial faults. Across the coupling, misalignment, across the machine, a bent shaft, another bent shaft, a overhung rotor unbalance, cocked bearings, inner and outer. So those are the directional faults that we're looking for. So my checklist, I'm going to go through the whole thing. I'm not going to, just because something's grayed off, I'm not going to eliminate it without putting it through a phase check. So I go and I look for unbalance and eccentricity, and I have certain rules that apply for that. I check for overhung rotor unbalance, and it looks like that's a possibility. In this case, the phase response is correct for an overhung rotor fault, but I don't know if the amplitude's going to figure into this. So I'm going to put a placeholder on that. That one's going to stay. I check for a bent shaft. The phase says nope, so I can take the bent shaft off the table. I check for misalignment across the coupling, and the table says, the bubble chart says nope, it's not out of alignment in the axial direction. And I look for cocked bearings, which are these faults top to bottom and side to side for each bearing housing, and they don't show any cocked bearing relationship. Okay, there's one more. I don't have peaks for it on the table here or in the bubble chart, but I can also check for soft foot if that's the case. Okay, so potentially I have one fault, an overhung rotor unbalance. I'm going to have to perform the diagnostic that's desired for the natural frequency. In this case, it's a little transient icon, and we'll do a little review of what that is. So I hit the machine with my rubber hammer in the X, the Y, and the Z direction, and it will show me the natural frequencies in the structure. The machine has to be turned off so that I can see the impacting that's going on. But these are two different natural frequency curves. So each peak is a natural frequency. You see the red dots. Each green dot in this case is the turning speed of the shaft. So 1 times RPM, twice times turning speed, 3 times turning speed. All these can have misalignment or looseness or something residual in the machine to excite a natural frequency. But we still need a couple of things. We need a natural frequency, and we have that. We have this green line and this blue line that have all the peaks on them. We must have a driving frequency. In this case, it's synchronous speed. My example, I could also extend to 2 times, to 6 times, whatever's in the peak in the spectrum can excite the natural frequency. So I'm going to look at them all. So in this case, I'm looking at 1, 2, and 3 times turning speed on each chart. And in this case, my 2 times is elevated. It is a source of energy, and it's within this plus or minus 10% range. Okay, so you have to have a natural frequency, a driving frequency, and a coincidence. And usually that's it's within plus or minus 10% of the frequency we're interested in. Okay, here's our real life thing, our synchronous frequency. We're looking for response at turning speed of the shaft, 1784. This shows me to be in the gully between these natural frequencies, as well as the horizontal as well as the vertical. So I don't have the appearance of a frequency amplification or resonance in this data. And I'm looking for a resonant peak at 1 times RPM because that's where I would find the fault. So what am I left with? I'm left with a logically sorted probable root cause. The only thing left on the table is overhung rotor imbalance. And I can go in there and do a little more phase analysis if I want, guarantee everything's to spec before I go tell my supervisor what fault I need to look for.